closely at this surface. Notice the microscopic variations in the mahogany, the exact depth of the scratches, and the precise distribution of dust. If you focus entirely on those microscopic details, you completely miss the larger reality. You are standing inside a library. In the 14th century, a friar named William of Ockham argued that the best explanation is usually the one with the fewest assumptions. Subtracting information, rather than adding it, gets you closer to the truth. Today, this logic is a strict mathematical requirement for artificial intelligence. Machine learning algorithms perceive our world entirely through data, but gathering maximum data doesn't guarantee maximum understanding. Often, it just creates maximum noise. This standard scatterplot shows a machine learning model's objective, drawing a simple, smooth trend line to capture the general pattern. But given too much mathematical freedom, the model memorizes the data, violently contorting to hit every single point perfectly. We call this overfitting. The algorithm memorizes random noise, the equivalent of microscopic desk scratches, instead of the underlying trend. Exposed to brand new data points, predictions fail entirely. The jagged line is completely out of position to guess where a new dot lands. A model that perfectly memorizes the past is mathematically doomed to fail in the future because it lacks the ability to generalize. To fix this, we have to change the rules of the game. We introduce a mathematical constraint called regularization, which adds a specific penalty term to the algorithm's loss function. Under these new rules, the model pays a complexity tax. It gets mathematically punished for every extreme parameter or heavy weight it tries to add to the equation. One common way to enforce this is L2 regularization, also known as ridge regression. This chart shows how ridge regression penalizes the squared values of the model's weights. Because large weights face an exponentially larger tax, that wild, jagged curve is forced to smooth out. The math pushes all the coefficients down to moderate levels. Ridge doesn't delete any variables, but it strictly restrains them. It ensures no single piece of noisy data has enough mathematical leverage to hijack the model's behavior. Sometimes shrinking the noise isn't enough. We need to completely eliminate it. That brings us to our second penalty method, L1 regularization, known as Lasso. This chart shows the weights of different variables. Lasso calculates its tax using the absolute value of those weights. It acts as a brutal editor, aggressively driving irrelevant features all the way down to zero. We call this feature selection. It is the mathematical equivalent of sweeping the irrelevant dust particles and desk scratches out of our dataset entirely. Lasso mathematically enforces Occam's razor. It proves that sometimes the best way to improve a system is to delete parts of it. To control the severity of these mathematical penalties, we use a hyperparameter known as alpha. You can think of alpha as a physical dial. It determines exactly how harsh the complexity tax will be on the model. This graph shows what happens if you make a common mistake, turning the dial too high. The model becomes overly penalized. It goes blind to the actual pattern and flattens into a completely straight, rigid line. This opposite extreme is known as underfitting, or high bias. The model is now too simple to capture the real-world pattern. We have to tune the dial back towards the center to restore balance. The core objective in training these algorithms is to carefully tune alpha, finding the exact sweet spot between overfitting the noise and underfitting the pattern. Regularization is a targeted process of stripping away the noise to arrive at a truth that is simpler and no less true. But to prove our model actually generalizes to the real world, we can't just validate our theory on one shelf. We have to check every shelf in the library.